Hi again, I'm Frankie, and welcome back to a video series about active learning. This is the third video in the four-part series where we are going to cover the choice of learning models and query policies within the context of an active learning algorithm. Learning models and query policies are really impactful in the way that the algorithm performs, and so we want to discuss of these learning models and query policies the advantages and disadvantages of how each one of these work. So the learning models that we'll cover include Gaussian processes and Bayesian neural networks, which are the most common models I've seen. And of the query policies, we're going to cover a diversity of different kinds of query policies that I think represent the range within all the query policies. So we'll cover uncertainty sampling, diversity sampling, query by committee, expected model change, and variance reduction. As a reminder, if you want more details about the general framework, the algorithm components for active learning, you can go back to video 2. But for your convenience, this is the general framework for active learning. These are the 5 different components that we really care about in active learning. And while we are going to cover learners and query policies in depth here, the reason why we're doing that is because in the problem statement for your application, these components, annotator and data, are pretty much already defined for you. If you already have a problem that you're interested in working on, it's very likely that your data is already defined. You already know what kind of input X and what kind of output Y you want to map between. And on top of that, the annotator, the ground truth system that generates the training pairs little d, which includes the x and y of your selected sample, that annotator is likely already chosen. And so the learner and the query policy, these are things that likely haven't been chosen yet, and you as a user, as a designer, can choose, and that choice then flows down into your algorithm performance. Let's start with the learner. So a learner is a model that learns a mapping, so the model being F, and the mapping being the transformation between this labeled input, X sub L, and target output, Y sub L. We talked about the different types of learners in the last video, and we decided that we are going to just focus on universal approximators in this video. The reason being is that we want this video to be as applicable to many of you behind the screen as possible, and so we want to be as data agnostic as possible. You can, of course, choose something that is domain specific where you're using your data to inform an F-hat or a function approximation, such as if you have a physics equation like Navier-Stokes, and all you're trying to do is tune the parameters that populate your Navier-Stokes equation. That is totally fine too. But for this case, we are going to use models that are as data agnostic as possible. So, of these universal approximators, there are a couple flavors. We can talk about Gaussian processes and Bayesian neural networks. Gaussian processes are a distribution over functions. And so what you're seeing here in this animation, on the horizontal axis is your input X, and then on the vertical axis is your output Y. And we're trying to find some mapping between X, the independent variable, and Y, the dependent variable. Let's say that we have 4 different data points, which are these 4 green dots. A Gaussian process is going to fit a distribution of functions to those 4 points. And so what you're seeing are the white curves are all samples of a distribution of functions. And these different samples can be characterized by some prediction, that light blue line, and then some credible region or uncertainty region, which is that blue shaded bound. Pictorially, that is what's happening, but mathematically, we can describe a Gaussian process with some kind of mean function, m of x, and some covariance function, k of x, and then x prime. So the mean is going to be that prediction line, and then that covariance is going to be that blue shaded region. Gaussian processes don't exactly have a training when it comes to incorporating new data into the model. There is training later on that we can talk about that is specific to the kernel, which is K of X. But for now, let's just talk about what an update of a Gaussian process model is. So to begin, let's say that you don't have any data. Well, a Gaussian process has a prior and a posterior, where the difference between the prior and the posterior is the update, is the incorporation of information. And so the prior, with no data going into this, for a Gaussian process, your function approximation for all of your unlabeled data is going to be some distribution with some mean 0 and some covariance k, and the inputs x sub u, where x is all of the inputs in the unlabeled domain. So you can see that this picture right here, this would be what a prior across the x and y of interest are. The three curves that you see here are samples of a distribution of functions defined by covariance k. And that gray region that you see, that is your covariance region. And so you'll see that there is a mean of 0 and a covariance likely of variance 2. Now let's say you get some data. Let's say that you get these 5 data points represented by those crosses. Well, the update, the posterior, will look something like this. So the prediction for the rest of the data points, so f hat sub u, so the function approximation for the unlabeled test points, conditioned on your test set, x sub u, your label data, so your training data, x sub l, and then the function approximation at the training points, f sub l, is going to be a distribution of, here's going to be your mean, where it's some combination of your covariance and your function approximation at your training points, f sub l, and then your uncertainty region or credible region is going to be defined by this covariance update, which is a combination of your covariance at the test points, at the between the test and training points, and then at the training points. And what I really want you to pay attention to is that the expression, the computational driver in this expression is going to be a matrix inverse of covariance. That is going to be the main thing that drives the computational intensity of this update step. With a little bit of rearranging, you can start to see that the mean function, or prediction for your unlabeled data, which is the expected value of your function approximation at your test points, takes this form, so just a little bit easier on the eyes, and your covariance, in this case we are looking at the variance, so the covariance at your unlabeled test data relative to the unlabeled test data is just the variance across each test point, is going to be the expected value of the variance between the function approximation at that point and the mean function. And again, nice on the eyes. So these are the equations that you would need to encode into your algorithm if you were to implement a Gaussian process. Earlier, we were talking about kernels. I just briefly mentioned it. And so kernels, K, are the building block of a Gaussian process. Just like how models can have basis functions, the Gaussian processes, their basis functions are kernels. And so in this picture of 6 different kernels, you can see that given the same data points, these blue dots, the kernel is going to fit a mean function and a covariance differently to the same data. And so this is really important when you are going into your problem and you're thinking about the, let's say, wiggliness or the behavior of that data, what that topology might look like. the selection of building block of basis function of kernel is going to fall out of your understanding of that landscape. The two most popular kernels that my lab has worked with, and I think the community has worked with, are these exponential, squared exponential, or another name for them are radial basis functions. Another kernel that's really popular is this Matern kernel, and the reason being is that these functions seem to be as data agnostic as possible, so regardless of the landscape, they seem to do really well in universally fitting the data that it's seeing. Whereas if you had a linear function that you knew that the relationship between input and output was linear, you could use the linear. If you had a periodic function, you could use something called a cosine kernel. Those pictures do have a mathematical mapping. So here is a table of what k of x, comma x prime could look like, where again, your squared exponential or radial basis function has this form. And we were talking about training earlier. There is a training to find length scales associated with these kernels. Length scales are a hyperparameter associated with kernels for Gaussian processes that you do need to tune with your data. Now let's talk about Bayesian neural networks. Bayesian neural networks offer uncertainty across a model output. And here we have a really similar diagram to what we saw about Gaussian processes, where you have some data, so these different dots, you have some mean prediction, so this light blue line, and then you have some uncertainty region, which is this dark blue shaded region. But you'll notice that even though the output looks very similar, there are some nuances in the output and also how that output was generated. You'll notice that in this dark blue shaded region, the boundary is pretty jagged, and the reason for that is that Bayesian neural networks are a lot more numerically driven, in which there are discrete activation events within the model that create this jaggedness. Whereas Gaussian processes are these probabilistic functions that have very smooth and elegant closed form solutions. So it has the smoothness that Bayesian neural networks don't inherently have because neural networks are very numerical. So let's talk about Bayesian neural networks. There is a relationship between Bayesian neural networks and neural networks that you may have seen in the wild already, like multi-layer perceptrons. So as a reminder, neural networks as a model are dependent on some input, some training data, and some model parameter. That's how they generate an output. So if this were your neural network, where the red bubbles are your inputs, and then these are the neurons of your hidden layer, and then this is your output, the weights and biases that represent these different lines take on a static value, a point value. There is some number that the weight and the bias will take for these signals. Now, Bayesian neural networks differ from that in that, let's see, this is a really similar diagram where inputs from the bottom and then output is at the top. So instead of the signals in your neural network being a point value, they are now a distribution. And that can happen in a variety of ways, which are shown here. You can have a probability or smear across values in your activation function, or in your parameters, which are your weights and biases, or across models. The way that the activation distribution is applied is that instead of, at your neurons, the activation function is a deterministic forward model. Instead, it's probabilistic. At the parameter distributions, so not at the neurons themselves, but the passing between neurons, instead of the weights and bias being a number that just forward passes in a deterministic way, let's make it probabilistic. Let's smear. And then for model distribution, instead of So in the model distribution, there are multiple neural networks that have point-wise values, but in their output, there is a distribution. So the way that we combine to that final output is we take a distribution across multiple models' outputs. Okay, so those are different ways that we can craft a Bayesian neural network. And in this paper, so you can find the paper link on the bottom corner right there. But to design a Bayesian neural network, yes, you have to have your data and the form of it, but then the actual training, there are many different training methods associated with Bayesian neural networks that are dependent on how they were designed in the first place. And so it depends on whether you have a shallow network or a deep learning network. It depends if you want to do Markov chain Monte Carlo training or if you want to do variational inference. So later in this video series, one of my students is going to talk about our implementation that uses Monte Carlo dropout and ensemble training. Anyway, the output, what's important is that the output of the Bayesian neural network is still very much the same that we've seen with Gaussian processes, where you have a mean prediction and an uncertainty associated with your learner. So, the choice of learners, maybe you've seen that the kind of implementation with your learner is going to impact the way the active learning algorithm works and then performs. And so different metrics associated with the inner workings of a learner include, say, the amount of data that you need to get a good model. So Gaussian processes work really well in the sparse data regime for low-dimensional problems. They are very structured and mathematically elegant, and so can offer a very elegant solution right away, whereas Bayesian neural networks, depending on the size of the model, the number of model parameters, that is going to then scale how much data you would need to come up with a good model. And this mimics the behavior of multi-layer perceptrons. So things that you have learned in that realm of neural networks also apply to Bayesian neural networks. For training computation, Gaussian processes don't really need much computation to train ahead of time. They just work in real time. They don't need to be seeded with much data to begin with, whereas Bayesian neural networks, you do need to seed them with a bunch of data. And so in training, before the model is deployed, the Bayesian neural network is crunching. On the other hand, during actual deployment, Gaussian processes do all of their work in real time. And so the computation is high associated with that matrix inverse. Whereas Bayesian neural networks, once they are trained, as you may infer from neural network behavior, the forward pass is very computationally cheap. When it comes to expressivity, Gaussian processes are very expressive inherently, being a universal approximator, but they can be limited by the kernel selection. And so we'll give Gaussian process medium expressivity, whereas Bayesian neural networks are highly expressive because you can scale the expressivity with the number of model parameters within the neural network. Moving on to query policies, this is the policy that describes where we should sample next. So again, your query policy is G, and it considers the learned model f hat in deciding where to sample next, which is defined by x at iteration I plus 1. We want to focus on query policies that stress exploration, where we are optimizing for information, which is described by some function I, over unvisited samples, which is the x, the input space in the data set that is unlabeled. This is a busy diagram, but it is just to show you that there are a suite of methods when it comes to different query policies. There are those that are for classification, for regression, and for clustering, but we are just going to cover the ones that are highlighted here. So we, as a Dynamics Institute, really care about regression, but there are some classification methods that can transfer over to regression. The ones that we're going to talk about are uncertainty sampling, diversity sampling, query by committee, expected model change, and variance reduction, because I believe these are representatives of a variety of ways of thinking about sampling. So let's get started on the first one. Uncertainty sampling is a policy that picks something that maximizes uncertainty. So you should remember this figure. This is the posterior of a Gaussian process where we've got our data points and then we've got our mean estimate and uncertainty region. If we were to inspect uncertainty across the independent variable region of interest, we can see that the gray region, or the uncertainty, is highest over here. And you can mathematically describe that with this equation right here, where uncertainty can be characterized by model variance, sigma, sigma squared specifically. And if we were to use Gaussian processes as the example, a Gaussian process directly outputs a mean and a covariance, where that covariance describes variance at that test point. Entropy is another way of describing uncertainty that the machine learning community really appreciates. And just as a reminder, entropy is the probability of y conditioned on x times the log probability of y conditioned on x. And this is across all of the unlabeled data. So you'd have to do this, you'd have to find entropy for all of the x and y pairs in the unlabeled data regime. What is convenient is that entropy and model variance are equivalent if the measurement noise has normal distribution. And so we can take what is appreciated about machine learning and just collapse it into a very simple calculation of model variance that typically falls out of probabilistic models. The next query policy is diversity sampling. And instead of inspecting a model output, we are inspecting the model inputs. We are trying to maximize disagreement across samples. And the way that we do that is here, pictorially. Here is a way of representing dissimilarity, where your horizontal axis is the first component in your input space. So let's say x1. And then the vertical axis is the second component of your input space, x2. If you were then to plot the different data points, let's consider these two candidates in the x1 and x2 components. The dissimilarity is the cosine distance between those two candidates. That can be described by this mathematical expression here, which you should be familiar with. It's the inverse cosine of the dot product between the unlabeled data point and the labeled data point divided by their magnitude. And so you want to find the dissimilarity across all of the unvisited points relative to the labeled data that you've already seen. For query by committee, instead of assuming that you only have one model to work with, query by committee, as the name suggests, means that you have a committee of models that you're considering. And so pictorially, here, the white points are the data, the orange line is the mean prediction of one model, and then the blue line is the mean prediction of a second model. You can find the mean prediction across these models, and that is your estimate that you put forth, the prediction of your ensemble of models. What you want to do in query by committee is to maximize the disagreement across the multiple models. And so if we look at this picture of the multiple models, it seems like the models most disagree probably at the boundaries over here. That can be mathematically described by this equation here, where you are looking at the prediction of each model, finding the difference to the mean prediction across all of the unvisited data points. This right here is an expression for model variance. and you, should get something that maximizes disagreement across the models with this query policy. For expected model change, we are trying to find the sample points that maximize the loss gradient over model parameters. Intuitively, you're essentially trying to find the sample points that are going to inspire the most change in your model. Here is a picture of loss as a function of model parameters. And what we're showing here is that, as your model updates, the loss is going to change, but the model parameters are the reason why the model changes. The lines here are the gradient of the loss with respect to the model parameters, theta. You can mathematically describe the loss gradient over model parameters with this expression right here, which is the partial of loss with respect to theta. And you want to find this loss gradient subject to the sample points that you haven't visited. So, if we were to break out that expression of loss gradient, it would look like this. And spoiler alert, this expression looks a lot like gradient descent if you're familiar with neural networks. So we'll use neural networks as just the example here. The expression for loss gradient is going to be the sum across the sample points that you're interested in evaluating. So the sum of the difference between the neural network output at those sample points and the actual labeled at that sample multiplied by the neural network's output gradient with respect to model parameters. So this model loss gradient is really nice in that if you have a neural network and you're training the model, your gradient should already be calculated in the training process. And so your query policy, if it were past that model and the training information, would already have access to information like this. The last query policy is variance reduction. And so this picture here is trying to show the difference between an update step, between iteration I, where the data is shown in this set, and then data at the next iteration where we chose this data point over here. And the whole point of this query policy is to minimize variance and subsequently expected error in the model prediction. So let's just inspect what happened between these two frames. The labeled data is in light blue, the unlabeled data is in white, the decision boundary that is true is that yellow decision boundary, and then what we think is that purple boundary. So what we do then, between what we see here and what we eventually pick here, is we pick this point right here because that moves the decision boundary in such a way that the variance of all of the blue points that we've sampled is squashed. And then that implicitly reduces the error between our estimated decision boundary and the true decision boundary. The mathematical way of describing that is with prediction variance, where you are trying to minimize the variance between your prediction and the true labels. Now there's a catch here. We've gotten ourselves into a bit of a pickle where this equation necessitates that you know the true labels of your unlabeled data set. And that's not possible. You can't read the future. And so really, when we implement prediction variance, authors have used Fisher information as a stand-in for prediction variance, where Fisher information is described by f of theta, where f of theta is the expected value of the second partial derivative of the log probability of your output relative to your input. Okay. So there are a lot of query policies, and there are many ways that they can impact performance. And so things that you should care about when you're selecting query policies are, what are the requirements on your learner if you were to select this query policy? Some query policies do not play well with some learners, and so we need to make sure that the interface, the point in which they're talking to each other and passing signals, is consistent. So for uncertainty sampling, you want to make sure that your learner is probabilistic in nature. For diversity sampling and query by committee, these policies are very friendly and don't require any requirements on the learner. For expected model change and variance reduction, you need to take a gradient with respect to, you need to have model parameters that you are able to change, so the model must be parametric. For simplicity, I think of simplicity as how easy is this concept to understand and also to implement in code. So for most of these concepts, these query policies, the mathematical equation that I showed you is very straightforward to encode in your algorithm. But for variance reduction, as we saw, it's not as mathematically straightforward, and so it's harder to code. For deployment computation, we spoke about this throughout the video, where certain evaluations kind of came along with the model output, but also some were computationally bottlenecked. So for uncertainty sampling, your model should already give you uncertainty across all of the predictions with its mean, and so uncertainty sampling is cheap. When it comes to diversity sampling, that depends. Diversity sampling depends on the dimensions of your input space, and it also depends on the size of your unvisited samples, because you need to do a pairwise comparison between all of your unvisited samples and your visited samples. So that could blow up with dimensionality. For query by committee and expected model change, you need to calculate the gradient or the variance across all of the unvisited samples, and so that can be quite expensive. And same with variance reduction. For guarantees, what I mean is there anything certain that we can say about the behavior of the algorithm? A symptom of guarantees are, say, like convergence. Does my model converge to some terminal value asymptotically? Well, for most of these models, there's not much literature about guarantees. So uncertainty sampling, diversity sampling, and expected model change, these are query policies where I didn't find any literature that proved model performance, or policy behavior. So maybe you could please come up with some guarantees. If you could do that, that would make the adoption of active learning much more broad. But thankfully, we do have some headway in query by committee. There's some theory about that, and variance reduction does have some empirical observations on guarantees. And finally, when it comes to how accurate your active learning algorithm is, query policies that directly optimize for accuracy are expected model change and variance reduction, and the query policies that indirectly optimize for accuracy are uncertainty sampling, diversity, and query by committee. And the reason being is that they don't directly optimize for accuracy in the optimization equation, but implicit in variance is then the subsequent improvement on accuracy. So let's evaluate as indirect. Just as a reminder, we talked about Gaussian processes and Bayesian neural networks as learners, and uncertainty sampling, diversity sampling, query by committee, expected model change, and variance reduction as query policies. I hope you enjoyed this video about how to choose learning models and query policies for your active learning framework. In the next video, we're going to talk about applications and limitations of active learning. The applications are going to be very explicit and what the different algorithm components are. And then we're going to talk about limitations associated with active learning so you can decide if active learning is a good fit for your application. See you in the next one.